Our second form of organic compounds would be lipids. In having already talked about carbohydrates, we mentioned that their main reason for importance in our body is that they are a direct source of energy. And yes, you can store carbohydrates for a reasonable amount of time as well. But when it comes to long-term storage of an organic compound to use as energy much further off in the future, that would be the lipids. Now again, lipids have other jobs besides that, but the main function for lipids would be that long-term storage of energy. Lipids, like carbohydrates, contain carbon, hydrogen, and oxygen. What is perhaps unique about the lipids is that they are insoluble in water. What does that word insoluble mean? Well, think back to when we talked about water and its polarity. We said water was adhesive. Other stuff would stick to it if that other stuff had a charge. Well, lipids lack a charge. There is no positive charge, there's no negative charge in the majority of lipids, and therefore there is nothing to attract them to either the positive or negative end of a water molecule, and they don't stick. You see the picture here of some salad dressing, and you ought to know what you do before you pour your salad dressing onto your salad. You shake it up, because different portions of it have separated from each other because they are insoluble. The oil in the salad dressing, which is an example of a lipid, will not mix with the water of the salad dressing. So as I just mentioned, oils are an example of lipids, but so too are fats, waxes, and even steroids. It's a bit of a catch-all category. Unlike the carbohydrates, which have basic monomers that are fit together to make larger versions of those carbs, there are two separate pieces that together make up a fat. Those would be glycerol, which is pictured here, and the fatty acids, which you see pictured here. Let's look at each one of those separately, but always remember you can come back to this picture to see how they're ultimately linked together. If we look just at the glycerol, there's not a whole lot to it. You've got your basic carbon chain or carbon backbone that all organic compounds have, and then radiating out from there, we've got just some hydrogens and hydroxides that are attached. Not a whole lot to it. The other portion of the fat, in addition to glycerol, is a fatty acid. And I think you've probably heard the term of saturated fats before, and perhaps unsaturated fats. Well, those terms really come back to what fatty acids compose those fats. If you look at this example here of what they're referring to as a saturated fatty acid, let's think about what the term saturated means. If I had a sponge and it was full of water, to the point that if I added one more drop of water, that drop of water would roll off. That sponge is saturated with water. Now, that's not exactly what this means here in terms of water, but the basic premise still remains. What is this structure just filled with? What is it saturated with? And the answer to that question is hydrogens. Look at them all. This thing is just full of hydrogens. So many that if you tried to add one more, there's just not room for it. Unlike an unsaturated fatty acid. Now let's look at this, and we've got to think about a little chemistry here. The key is what looks like this red equal sign here. That's not an equal sign here. In this case, that represents what's called a double bond, a chemical bond that there's two of them. So what we talked about earlier is that every carbon has to have 4 chemical bonds. And you can see if we look at this carbon here, 1, 2, 3, and 4, radiating out in all 4 different directions. Well, this carbon here has 1, 2, but then it has 3, 4, both attached to the carbon next to it. And so that's referred to as double bond. Well, what's the impact of that double bond? Because these 2 carbons are attached to each other twice instead of once, that eliminates 2 hydrogen atoms. There could have been a hydrogen down here below this carbon, and there could have been a hydrogen down here below this carbon, as is the case up here, but because of that double bond, that eliminates the possibility of those 2 additional hydrogens, and therefore this thing is not filled with hydrogens, it is unsaturated. And we could have more double bonds. I know there is only one pictured in this particular example, but there could be a double bond here, in which case 2 more hydrogen atoms would be eliminated. Maybe there would be a double bond here in which 2 more hydrogen atoms would be eliminated. And so the more double bonds, the more unsaturated this fatty acid becomes. And so if we think back to our picture here, you can see the lipid as a whole, the fat, with its glycerol on the left and 3 fatty acids attached on. You can see a saturated fatty acid there, a saturated fatty acid here, and an unsaturated because of the double bond here attached on. This particular fat is formed by attaching these 3 fatty acids to this glycerol. The question then becomes, well, how? How did they attach? How would you take smaller organic compounds and attach them together to make something larger? You should already know the answer to that. It is dehydration synthesis. This fatty acid is attached to this glycerol because a dehydration synthesis reaction occurred. Same thing here, same thing here. The other thing to discuss here is this idea of saturated and unsaturated. Just as a general rule of thumb, one of the things that you probably ought to be aware of is that when a fat is very saturated, it tends to be solid at room temperature. Think like bacon fat, lard, things like that that are solid at room temperature are very saturated fats because they have very few double bonds, they have a whole lot of hydrogens. The more liquid something is at room temperature, the more unsaturated it probably is. In other words, there's a bunch of double bonds, and therefore the elimination of a bunch of hydrogens, and it becomes more liquid as a result. Think vegetable oil.